Hello, this is the first in a series of videos I'm doing on the topic of random number generators, particularly random number generators in computers. Now I have been working on random number generators for the past 12 years or so. I developed the random number generator that is in the Intel chips. And also a number of other random number generators which go in other contexts, and I've reviewed many other random number generators in other products and worked on testing algorithms for random number generators. And then I went and wrote a book. That's this book here, Random Number Generators, Principles and Practices, by me, David Johnston. So the goal in that book was to dispel a number of misconceptions about random number generators that you find commonly across the internet, and help people who are using them in software and engineering understand what they would need to do to have a good random number generator, or evaluate random number generators they might be using, say that they're buying from IP places, things like that. So there are many topics to cover, and I'll be trying to cover most of them. I'm going to try and make each of these videos about 20 minutes in length, but this is the first of them. The first video is going to be about terminology, because we find in the field of random number generators the terminology is pretty messed up. You have terms like true random number generator. What does that mean? And you look at the definitions, there are many different definitions, and when people use it, you don't know what they really mean by true. What does true mean? True means something's correct or something that happened, but true random, what does that mean? Does it mean it's non-deterministic? Does it mean it's perfectly uniform? Things like that. And the answers to that get quite deep into things like quantum physics and extractor theory, and when you go and read the papers about such things, the mathematical academic papers, they are deeply mathematical, using mathematics that most people, even computer engineers, even software programmers, they don't know that mathematics. I only partially know that mathematics. I had to learn it in order to read the papers. But that was one of my reasons for writing the book, was to get over those concepts that were in those papers, so that it was possible for people to make good choices about using random number generators or creating random number generators or things like that. So here we start on the first topic of terminology for random number generators. Okay, so I've now got up a terminal into which I can write commands, and we're going to use a couple of tools to help understand the terminology. So first, let's look at a couple of random number generators outputs. So here's a program called genrandom, and we run that, and we get out some data, some random data. Now it's and if you look at it, it looks random. Now if you squint, you might see some kind of patterns, but that's just your human visual system picking up patterns that aren't really there. If I do this again with -s, we get a different set of numbers out. And in fact, with this option here, what we are getting is random numbers that are called full entropy. That means every single bit of data making up this is hexadecimal data on the screen, so per character there are 4 bits of binary data, and every bit of that data has a 50% chance of being a 1 or a 0, and there is nothing about any of the data coming out that tells you anything about any other data. So if you look at, say, this line, the first line to come out after we ran this program, that's 256 bits of data in that line, and there is no amount of computation you could do, no amount of work you could put in to get that data to tell you anything about the second line. The second line coming out has nothing to do with it. The first line, it's called independent. And it's true of every bit. No amount of data in there tells you anything about the state of another bit. And also they have a 50-50 probability of being a 1 or a 0. So this touches on another property called IID, or independent and identically distributed. So identically distributed is the same as saying every bit has a 50% chance of being a 1 or a 0. The full entropy part is about is defined in terms of the probability of the most probable symbol. So the symbols are 1 and 0 in this case because it's binary data. And we're presenting it as hexadecimal, but it's really binary. And so the most probable 0, well, there are two symbols and they're equiprobable. There's a 1 and a 0. They both have the same probability. So we could say that distribution, 1 and 0, is uniform. There's another term, a uniform distribution, means every outcome of the events is equally probable. So we have this full entropy data, and full entropy roughly means it has all the nice properties we want of perfect random data, and it's usually what people mean when they call stuff true random data. But I don't like that term. I much prefer to use the correct terms. So this is non-deterministic. If I run this again, I get different data, and the reason I'm getting different data is because it's coming from a physical process that is leading to it being different every time. It is uniform, statistically uniform, and it's independent. So those are properties we've got for this data. Now, if I do another a different model, so this program gen random has different models, and I'm going to do this model, PCG, and this stands for permuted congruential generator. It is currently the best of the non-cryptographically secure pseudo-random number generators. So there's another term, non-cryptographically secure versus cryptographically secure. This looks random as well, and I'll run it again and you get some different data. And in fact, if looking at this and you were doing statistics on this, you would not be able to tell the difference between that full entropy data and this data. But this is absolutely not full entropy. This has about 64 bits of total entropy in it, meaning the state of the algorithm, this PCG algorithm, is a 64-bit number, and that determines what the next state of the algorithm is, what the output of the algorithm is. And if you were to reset the PCG to have the same starting state, so something like this, starting off with 8F24, we could run it again, and we'll get the same sequence out. And in fact, this first 64 or so bits of data, if you knew the internal state that led to that data, you could compute what all the rest of this data coming out. So that is a pseudo-random number generator, as in it is not non-deterministic, it is deterministic. It is statistically uniform. The PCG has very good statistically uniform properties. It looks very random. There's no bias where one symbol is more or less likely than another. And there has been a lot of research over the years into this kind of algorithm. And if we looked at the full entropy data here, this has pretty much the same properties, other than there's full entropy. Every bit contains 1 bit of entropy. With this, there's only a limited amount of entropy in the data, regardless of how much data comes out. And so this is a pseudo-random number generator. It is deterministic. It is statistically uniform. So there are some other terms we might use to describe a particular kind of of random number generator, and I'll do a last type of random number generator, and this time a linear congruential generator, LCG. Now this is what we generally consider to be an awful random number generator. It still looks random. Some of the statistics of this look equally as good as the other two, but it is deterministic. When I run it again, I'm going to get the same results, and it's certainly not secure in any way. You can, from the output data, not the internal state of this generator, but the output data, you could look at this data and compute everything else that comes out. So it is in no way secure. You just need to see a small amount of the output and you can compute the rest of it. So what separates these things, in terms of, well, why don't we just use the best one? Why don't we use the full entropy output? Well, one, sometimes you want repeatability, so you would like a deterministic source and a restartable source. But also to get the full entropy data, there is a lot more computation involved. So let me do another command, quick rdrand. So rdrand is an instruction in Intel CPUs. I'm running this on an Apple Macintosh, which has an Intel CPU in it. Now, as you may know, future Macintoshes are going to use an ARM-based CPU, and one of the things you will not be able to do on that is run. Whoops. Let's do this right. Quick rdrand is run this command. Quick rdrand -k 10240 O. Okay, so we run that, and now it's gathering 100 megabytes of data, and that took 3.78 seconds to collect 100 megabytes of random data, and send it through the operating system interface that throws it away. Now, if I add this extra option -s, what this says is use a different instruction called rdseed. And what rdseed does is coming out of the same random number generator, but a different path, which leads to it being full entropy data. So we'll run that, and it'll take a few seconds. And it's taking some seconds, and it's taking some more seconds, and you'll notice by now it's taken longer than it did before. And in fact, it took 10 seconds to run. So that's interesting. It took us roughly 3 times as long to create this full entropy data as it did to create the cryptographically secure but pseudo-randomly generated data. And what's going on there is the non-determinism is coming out of a hardware process which is limited in speed, but the pseudo-random number generator is built in hardware and is designed to be as fast as possible. We threw a lot of logic gates at making this thing run fast, and then the non-deterministic random number generator is trying to reseed it as fast as possible to enhance the security in a way that makes it, let's say somebody came up with a better attack against that algorithm, which meant that you didn't need to do as much work to predict the output. Still, you'd be wasting your time because it was reseeded frequently. So that's a design of a cryptographically secure random number generator. It's using both aspects of non-determinism and cryptographically secure algorithms to create cryptographically secure random numbers. But we find that the better data, in the sense that it's full entropy, is data which takes longer to generate. Okay, so finally a quick review of the words we've looked at, and in the next video we'll go on to some more terminology. So deterministic versus non-deterministic, uniform versus non-uniform, cryptographically secure versus not cryptographically secure, full entropy versus partially entropic, IID or independent and identically distributed, uniformly distributed, a pseudo-random number generator, and the instructions rdrand and rseed. That's it. Thank you and goodbye.